Bismillah Rahman Rahim. In the last lecture, we have discussed the half bridge single phase square wave inverter in detail. We discussed the operation of the square wave inverter with the resistive and the inductive load. So, in the half bridge inverter, we have a DC source, and that DC source is separated into two parts in two equal voltage levels with the help of these capacitors. Two switches are used. These switches may be the IGBTs or the MOSFETs. IGBTs are used for medium frequency high power applications, and MOSFETs are used for high frequency medium power applications. So, we have two switches, and with the help of these switches we can convert this DC voltage into a square waveform. Means two voltage levels, a positive voltage and a negative voltage at the output of your inverter circuit. So, the load is connected between the center point of these two capacitors and the switches. This is the arm of the switches, and in this arm we have two capacitors. So, when we turn on the switch S1, this capacitor is connected across this load. So, this is the positive terminal, this gets connected with this point. So, this will be a positive potential, and this point is connected with the negative terminal, because this DC source is first divided into two parts, VDC by 2 plus minus VDC by 2. So, once it is divided into two parts and we are going to turn on the switch S1, this capacitor will be connected in parallel to the load. So, your load voltage will be equal to VDC by 2, that is this one. When you turn off this switch and turn on this switch S2, turn it off, then you will be turning on the switch S2. So, if you have the resistive load, this point will be connected with the positive terminal, that is the positive terminal of the source will be connected with this point of the load. So, this point now will be positive and this will be negative, because your switch is going to connect this point with the negative terminal of the source. So, your load voltage will be plus minus, that is the opposite with respect to the first case. So, when you apply the gate voltage VG1 to this switch, right, so this VDC voltage, VDC by 2 voltage is going to appear across the load. So, this is the load voltage waveform, and then for the rest of the half cycle Ts by 2, you are going to turn on this switch by applying the gate voltage at the gate of this switch, and once it is turned on, the load voltage is minus VDC by 2. So, the duty cycle is 50%. If you look at this waveform, for 50% of the time your switch S1 is in the on state, and for rest of the 50% of the time it is off, then it is turned on again, and then it is turned off. So, we have the 50% duty cycle of the gate voltage of the switch S1. Similarly, if you look at the gate pulse or the gate voltage of the switch S2, it is off for the 50% of the total time, and then it is on for the 50% of the rest of the time. So, its duty cycle is also 50%. So, we generate two gate signals each of 50% duty cycle, right, and we apply to these switches S1 and S2. So, whatever is the shape of your gate voltage that appears across the load. So, in simple words, you can say that your inverter is basically an amplifier, a class D amplifier. So, if you look at this voltage and compare it with this one, so you have the same shape. So, let me highlight it like that. You are going to apply this gate voltage, and you are going to get this one as the load voltage. So the magnitude of the load voltage depends upon this voltage, the voltage across this capacitor, right? So we can say that this is going to act as a class D amplifier. So we can model the inverter with the help of the simple gain K, the gain between Vg1 and the V load. So when you apply the gate voltage, right, the same wave shape appears across the load. So over here we have the main source. So load voltage will be set according to the main source voltage, and I am calling this voltage as the main source voltage. So whenever you apply the gate voltage Vg1 to this switch S1, this voltage will appear across the load. This source voltage will appear across the load, and the wave shape at the load will be according to this gate signal Vg1. Okay, so our voltage waveform across the load will be having the positive as well as the negative area that you can observe over here. Why it will be having the positive and negative area? Because you are making the polarity opposite with the help of the switch. When the switch S1 is on, this point is positive, this point is negative, and when this switch S2 is on, this point is positive, this point is negative, because you can see this supply is connected with the load. But you cannot turn on these two switches together. If you turn on these two switches together, you will be short circuiting these capacitors, or you will also be short circuiting these the supply. So you cannot turn on S1 and S2 together. So they are operated in the complementary mode. Means when this switch is in the on state, this will be in the off state, and when this will be turned on, this is to be kept off to avoid the short circuiting of your source. So usually there is a dead band that is introduced over here. Means when you are turning off this switch, you will have to ensure that it is completely turned off. The practical switches take certain time, that is usually a very small, it is in the range of nanosecond, maybe up to few microsecond to turn off. So you will have to generate a delay over here at this point over here, so that there is no short circuiting of the source. This S1 is completely turned off, then you are going to apply the gate voltage to the switch S2 to get turned on. So I can draw the gate signals like that there is a small delay when we are going to apply the gate voltage to the second switch. So this is said to be the dead time, and that is introduced to avoid the short circuiting of the two switches of the source, sorry. So if both of these switches will be turned on, your source will get short circuited. So we introduce the dead time between the transition when we are transiting from S1 to the S2. Now if you have the resistive load, your voltage and current waveform will be of same shape that you can see over here. The current waveform is exactly of same shape as that of your voltage waveform. The magnitude of the current waveform will be simply equal to VDC by 2R, because you are applying the VDC by 2 and the load resistance is R, so you will get this current waveform. So if you are going to switch on this switch S1 and S2 for equal interval of time, then the area covered in the positive cycle and in the negative cycle will be same. So there will be no DC component. The DC component will be 0 if you have the equal positive and the negative area in the voltage waveform. So if there is no DC component, there will be no saturation of the transformer if you connect that transformer as a load over here, right? And for AC loads, there should be no DC components. So if you keep this area equal, positive and negative area equal, so your DC component at the load will be 0. Okay, then we have discussed this half bridge inverter with the inductive load. If you have the inductive load, then you will be requiring these diodes for the dissipation of the energy that is stored in this inductor. So now let's look at the detailed operation of this circuit briefly again. So first of all, if you are going to turn on the switch S1, so this will be the loop of the current. The current is going to flow in this loop and the energy will be stored in the inductive part of the load, and that energy will be equal to half Li square. And your switch will be conducting, and this is the unilateral switch, it can conduct only in the one direction. So the current will be building up in this mode of operation when your switch S1 is in the on state. Now once you turn off this switch S1, the energy stored in the inductor, half Li square, needs to be dissipated. So this inductor, because of the rate of change of current, will give you an induced voltage across its terminals, because inductor voltage is equal to L di by dt, and you are going to interrupt the current. So depending upon the rate of change of current, there will be a voltage across the inductor terminal, and that will be with the opposite polarity with respect to the voltage that was there before the interruption of the current. So when you are going to turn on the switch S1, the voltage over here is positive, the voltage over here is negative. This is the voltage polarity across the load. But once this switch is turned off, so you are going to interrupt the current in the load. So this point is going to become as positive and this is going to become as negative, and because of this negative voltage over here, this diode will be turned on, right, in order to maintain the same direction of the current through the inductor, because the direction of the current cannot be changed immediately through the inductor. Inductor resists the change in the current. So now let's look at this loop. Once you are going to turn off this switch S1, so the direction of the current in the load is to be kept same. It was flowing in this direction, so this will take this path through this diode back. Now this inductor is going to work as the source. Over here it was working as the load. It was absorbing the energy, it was storing the energy, sorry. And once you are going to turn off the switch S1, so the energy stored in the inductor, that is half Li square, will be dissipated because of the flow of the current in this loop. That will be dissipated across the load resistance, right? So this inductor will be acting as the source of the energy when you are going to turn off this switch S1. So when this switch S1 is in the on state, this is the path of the current, and when it is turned off, the path of the current is basically this one, starting from here through the diode, through the load, back to the source. So you are shifting this energy half Li square to the capacitor, right, and will be some portion of that will be dissipated across the resistance of the load, and some dissipation across the on resistance because of the on resistance of the diode across this diode D2. Okay, once you are going to turn on the second switch S2, and that will be turned on when the uh, energy that was stored in the load has been completely utilized. So then how the current will develop in the opposite direction? When you will be turning on S2, once the current becomes 0, I am assuming that inductor current has become 0 over here. So once it becomes 0, then if your switch S2 is on, means you have applied the gate voltage VG2 at the gate of the switch. So then the current is going to develop in this direction. This is the loop of the current, because this switch is turned on and the current is going to flow like this. So now this will be acting as the source. It will be storing the energy in the load, and the current is going to flow in this loop. So your inductor is going to act as the load in this case, right? Okay, once you are going to turn off this switch S2, the polarity across the inductor before the turn off of this switch is when this switch S2 is in the on state, this is positive. Why? Because it is connected with the positive terminal over here, and this negative terminal is connected over here. So this is the voltage polarity. But once you are going to interrupt the current in the inductor, so this point is going to become positive and this is going to become negative, that you can see over here in this diagram. And because of this positive voltage, this diode is going to be turned on, and this will be the path of the current, because the direction of the current through the load is to be maintained, right? So depending upon the rate of change of current, the inductor voltage will be there. So inductor voltage, that is equal to L di by dt. So if let's suppose that you have the 200 volt over here with respect to this reference point. So when there will be a high rate of change of current, the voltage over here, let's suppose, goes to 201 volt. So then this diode will be turned on and this path of the current will be established, right? So now just look at the gate pulses which we are going to apply. First of all, you are going to apply the gate voltage to the switch S1, and again the duty cycle is 50% over here. For 50% of the time you are going to apply this gate voltage to the switch S1, and for the 50% of the time it is in the off state, the switch 1, right? And the second switch is being operated in the complementary mode. When the switch S1 is off, switch S2 will be in the on state. So gate pulses are same as that we used for the resistive load. So our output voltage when VG1 is there, means when switch S1 is there, and for that our output voltage is VDC by 2, and when switch S2 is on, so our output voltage is minus VDC by 2. Okay, so when you have the positive voltage across your load, in the very first cycle the current will be starting from 0 and it will be building up like this, right? So this will be the current through the switch S1 in the very first cycle. So when you are going to turn off the switch S1 and you are going to apply the gate voltage to the switch S2, so you are basically in this mode of operation. In the second mode of operation, you have turned off this switch and you have turned on this switch, but there will be no flow of current through this switch. Why? Because it's a unilateral switch and the direction of the current through the load is this one in this mode of operation. So this cannot conduct in the opposite direction. Only this diode will be conducting and will be providing a path for the dissipation of the energy. So even you apply the gate voltage to this switch S2, but the direction of the current is like that, so it cannot conduct. So the path of the current will be like that, and D2 will be conducting. So D2 will be conducting up to the time till the whole energy that was stored in this inductor, half Li square, is dissipated. So that you can observe over here in this waveform. So assuming that in the very first cycle you have stored the energy in the inductor, and the current at the end of the cycle was this one. So when you are going to turn on the other switch, the load voltage is going to become negative, and the inductor is going to act as the source. So the energy of the inductor will be dissipated through the diode D2, and then the current will start building up in the opposite direction, and the switch S2 will be conducting. Over here the current becomes 0. Now you can develop the current in the opposite direction. So when the switch S1 was conducting, this was the mode. When you are going to turn off the switch S1 and going to turn on the switch S2, you are in this mode, and diode will be conducting for the dissipation of the energy stored in the loop. So once that current goes 0, you will be in this mode. Now the current will be developing in the opposite direction in the load through this switch S2, and now this will be conducting. So first S1 is conducting, then D2 is conducting, then S2 is conducting, and once you reach to this point, the current develops in the opposite direction. Let's suppose to this value, and that is the end of this cycle. So you are going to remove the gate voltage from the switch S2, and you are going to apply the voltage at the gate of the switch S1. So you will get the plus VDC at the plus VDC by 2 at the load. So because of that, your diode D1 will start conducting, and once the current becomes 0, then the current will be developing in the opposite direction, and then your switch S1 will be conducting. So if we replicate this one over here, so for the some time the diode D1 is conducting, then S1 will be conducting. Once you turn the switch S1 off and apply the gate voltage to S2, first D2 will conduct, and once the current becomes 0, then the current will be developing in the opposite direction. So our current waveform will be somewhat like this for the inductive load. So let's suppose that the minimum value of the current is I1, and the maximum value of the current is I2. So as we have the 50% duty cycle, so for 50% of the time we are going to apply the positive voltage, and for 50% of time we are going to apply the negative voltage. So there will be a symmetry in the current waveform. So the current waveform will be like that. The positive peak will be equal to the negative peak. So we can write that at I2 is equal to minus I1, or I1 is equal to minus I2. If you know one of these one, the maximum value and the minimum value, so you can work out the other ones. There is this symmetry, and there will be the symmetry in this waveform. The positive area and the negative area that of this current waveform, both of them will be equal, because the 50% duty cycle of the voltage waveform, and it is also dependent on the time constant and the that is the tau is equal to L by R. So the current also depends upon that one. We have derived the detailed expression for the current in the last lecture for this half bridge inverter circuit. Okay, now let's quickly look at the full bridge inverter circuit with the inductive load. In the full bridge circuit, instead of using the two switches, one arm of the switch, we are adding the second arm as well. So we have the two arms of the switches. One is this one, the first arm. In each arm we have the two switches, and this is our source. So we are using two arms, and the load is connected between the center point of the two arms. So this one is the load, right? So now let's look at the operation of this one. So we have four switches over here. First of all, S1, S2, these are the two complementary switches. S1 and S2 means when you are going to turn on S1, you cannot turn S2. And these two switches, S3 and S4, these are the switches of this arm and cannot be turned on together. If you are going to turn on S1 and S2 together, there will be a short circuiting of the source. And similarly for S3 and S4, if you turn on them, there will be the short circuiting of the source. Okay, so in the first mode of operation, what is done? We apply the gate voltage to the switch S1, and at the same time we are going to apply the gate voltage to the switch S4. So if these two are on, so from here the current will flow like that through the load, through the switch S4 back to the source. This will be the path of the current, and your load voltage will be equal to your supply voltage, that is VDC, because this point is connected with the positive terminal and this point is connected with the negative terminal. I am going to assume that this is an ideal switch and there is no voltage drop across this switch. In that case, whatever is your this source voltage, that is going to appear over here, and similarly this point will be connected over here. But in the practical cases, because of the high if there is the high current and there is the internal resistance in the on state, that is RDS, drain to source resistance, on resistance of your MOSFET or the power switch, so there will be a heat loss across that one, I square R RDS, right, and there will be a voltage drop as well across this resistance, voltage drop across this switch. So the load voltage will be slightly lesser than the source voltage, right. So you will have to use two switches over here to complete the path of the currents, and that path is this one as shown over here. So this is the path of the current in the first mode of operation. So when you are going to turn off any one of these switches, S1 or S4 or both of the switches, and how to turn off? By removing the gate voltage. So what is going to happen? The energy was stored in this inductor, that is half Li square. So that energy will force this inductor to act as a source. In the case when your switch S1 and S4 are on, your inductor is going to act as the load and storing the energy, and the energy stored is half Li square, right. So when you are going to um, turn off S1 and S4, so what is going to happen? Before the turning off, this point is positive and this point is negative, but once you turn these switches off, the inductor will apply the opposite polarity. This point will become positive and this is going to become negative. And you can also say that you are going to turn on S3 and S2. So because of that, you can say this point is going to be connected with the positive terminal of your source, and from here it is connected with the negative terminals of the source. So that's why I'm going to say plus and minus. Okay, so but the direction of the current through the inductor is this one in the first mode of operation. So it cannot be reversed immediately until and unless the whole of the energy stored in the inductor goes to zero, is dissipated. So this positive voltage is going to turn on your diode D3, right, and this negative voltage is going to turn on your diode D2. So path of the current will be like that, through the diode, through the load, through this diode back to your source. And the direction of the current that you can see is same, whatever over here same is over here, but over here this was acting as the load, and over here your inductor is going to act as the source, because the energy stored half Li square is now being delivered back to the source, or is being dissipated in the loop of the current, right. So our voltage is negative in this part with respect to this one. If we say the voltage over here is positive, and let's consider this direction of the current as the positive direction, so current and voltage both are positive when you are going to apply the gate voltage on switch S1 and S4. And as your voltage is positive, current is positive, so we are going to consider that power is positive, and power positive means it is being delivered from source to the load, right. So this is the source part, and over here through the switches we are connecting the source with the load, and the power is going to flow from source towards the load. But once you turn off the switches, the diodes turn on, so the direction of the current through the load is exactly same whatever over here, but the load voltage polarity is opposite. and with respect to this one, so we can say that that voltage has become negative, the current polarity, the current direction is same. When the switch S3 and S2 are turned these two switches S1 and S4 are turned off, and S3 and S2 are turned on. So once they are turned on, but they are not conducting. Why they are not conducting? Because they conduct only in one direction, because these are the unilateral switches. So they cannot they can only conduct in this direction over here assumed, and they cannot conduct in the opposite direction. So because of that, the diodes are providing the path for the flow of the current, right? So in the case of the MOSFET, as you would have studied in the basic power electronic course, this diode may be the body diode, but in the case of IGBTs, you may require the external diodes to be connected across the IGBTs, and in some packages the diodes are built in within the same package of the IGBT, because these are essentially required for the inductive load, because whenever you are going to turn off the switches, the energy stored in the inductor needs to be dissipated somewhere. So for that your diodes are essentially required. Otherwise, what is going to happen, because when you are going to interrupt the current through the inductor, let's suppose you are going to turn off this switch and this switch, so you are interrupting the current. And if you do not have these diodes D3 and D2, so what is going to happen then? The initial polarity is plus minus, and the new polarity across the load because of the interruption of the current is opposite. So because inductor voltage is given as L di by dt, and according to Lenz's law, um, the polarity should be opposite over here. So because of this very high positive voltage that you are going to apply across, let's suppose, the source of this MOSFET, so if that is higher than the reverse breakdown voltage of your switch, so then your switch is going to be permanently damaged. So just like your diode, we have discussed it before, that your diode characteristics are like this. These are the forward characteristics, and in the reverse direction it is like that. Reverse breakdown voltage VBD, let's suppose, that is very high. The forward voltage is normally in the range of 0.7 volt for the silicon diode. So once if you apply the very high negative voltage, so there may occur the breakdown, the avalanche over here, and that can cause the failure of your diode. So same is the case over here. If you are going to apply the very high opposite voltage across the switch, that is beyond the breakdown capacity of your switch, then your switch is going to be damaged because of the excessive flow of the current through the switch. A high amount of energy will be dissipated, and then that can cause the permanent damage of your switch. So the first mode of operation, the switch S1 and the S4 in cross, they are turned on, these ones, right? And then your diodes are going to be turned on automatically for the dissipation of the energy that was stored in the inductor to maintain the direction of the current through the inductor. So these diodes are essentially required, and will help the smooth operation. Once the whole energy is dissipated, then your switch S3 and S2 will be conducting, and now the path of the current will be like this, because the current has become zero in this mode of operation, and now this terminal is connected with the positive terminal of the source, and this one is connected with the negative terminal of the source. And now as the current is zero in the inductor, so now it can develop in the opposite direction. So the path of the current will be like that. It is through the switch S3 and through the switch S2 in this third mode of operation. And now the energy is being pumped in the inductor, that is half Li square, but with the opposite current with respect to this case. So now if I look at the voltage and current polarity, over here the voltage was positive, the current was negative, so your power was negative because your inductor was acting as the source of energy. This was acting as the source, right? So that's why we are going to say that the power is negative. Now over here the voltage polarity is this one, this is plus, this one is minus, right? This is one is plus, this one is minus. So opposite with respect to that one. So we can say voltage is negative and the direction of the current is like that. Over here it was in this direction. So direction of the current is also negative. So what about your power? Power is the product of the voltage and the current. So the power is again positive. What that means, that is being delivered from the source to your load, right, through these switches, and these switches are conducting in the downward direction. Considering the MOSFET from drain to source is the flow of the current, right. Okay, so this is the third mode of operation, and now if you are going to turn off the switches S3 and S2, so the polarity across the inductor will be like that. This is going to become positive and this is going to become negative. This point is positive, this point is negative, and the current was flowing in this direction, right. So because of the positive voltage, your diode D1 will be turned on, and this will be the path of the current, and because of the negative voltage over here, your D4 will be turned on. So this is the loop. So the current will be flowing through your inductor and through the diodes, through the source, and will be completing the loop like this, right. So the energy that was stored in the inductor over here, half Li square, when the inductor was acting as the load, it was storing the energy, it was taking the energy from the source. But now over here in this mode, this is going to work as the source, because it is providing the stored energy through these diodes back to the source, and that is also being dissipated across the resistance of the loop. So now over here, if you look at the voltage polarity, this is plus minus, and it is exactly same as that of, so our voltage has become positive. But what about the current direction? Current is going to flow in this direction, and over here it was in this direction, right. So the direction of the current is opposite, so we can say that voltage is positive and the current is negative, so power is negative, and it means this is going to work as the source, and it is delivering the power through the diodes back to the source. So in the full bridge inverter circuit, we are going to use two arm of the switches as compared to the half bridge inverter, or you can say you are going to use two half bridges. This one is the half bridge, this is representing the half bridge, and this circuit, because of its shape, if you look at that one, you are going to turn on these two switches, and then you are going to turn on this pair of the switch. So its shape is like the H. This is one is your load, and these are your switches S3, S4, S1, and the S2. So it is also called commonly the H bridge circuit, right. So over here we have the positive power, over here we have the negative power, again the positive power and the negative power. Negative power means your inductor is going to work as the source, and the energy is being fed back from the load towards the source, and the positive power means the energy is being pumped from the source towards the load, right. So now what is the advantage of using four switches? You were getting the square waveform with the half bridge as we discussed over here, and if you look at the waveform over here in this, so what you will be getting at the output, when you are going to turn on the switch, this S1 and S4, you will get positive voltage across the load, right. And when you are going to turn on these switches S3 and S2 again, and you will be getting opposite voltage with respect to that one for that interval of time. So if I look at the waveforms, the waveforms will be exactly same. You are applying the gate voltage to S1 as well as to the S4. So I am going to write it over here, S1 plus S4. You are applying this gate voltage, and instead of getting VDC by 2, you are going to get VDC, double voltage, because over here just look at this circuit, VDC, when this switch is turned on, this VDC is connected across your load. In the half bridge inverter, we were splitting that voltage, we were dividing that voltage into two parts with the help of these two capacitors. But over here we are not dividing this voltage, rather the whole of this VDC is applied across the load. So load voltage will be equal to VDC. double as compared to your half bridge inverter, and that is the biggest advantage of the full bridge circuit, H bridge circuit, that you will be getting the double voltage. You are utilizing this voltage source efficiently, effectively, because if you are using this circuit, the source voltage is VDC by 2, VDC, but the voltage across the load is VDC by 2, because you have separated that VDC into two parts, VDC by 2 and the VDC by 2, and in each half cycle the voltage across the load is VDC by 2, the half of your source voltage. But if you look at the full bridge circuit, for any mode of operation, either this one or this one, when switch S1 and S3 are on, your source is connected with the load with the full voltage VDC. So the power that is being transferred from the source to the load, that will increase, that will become double. You are going to effectively use the voltage source. So that's why your full bridge inverter circuit is used as compared to your half bridge circuit. We use two more switches as compared to half bridge, but we are going to utilize the source effectively as compared to the half bridge inverter circuit. Okay, so now let's quickly look at the combinations those are available. So we have four switches, S1, S2, S3 and S4. So these switches are the high side switches, this one and this one, or you can say the switches which are connected with the positive terminal of the source. Those are called the high side switches, or the switches in which the drain, I am considering these switches as the MOSFET, so the drains are connected with the positive terminal of the source, and the source terminals are not common, right? As you can see over here, if I consider this one drain, this one is the source, drain and the source. So drains are common, source terminals are not common. Drains are common and connected with source. So those switches are the high side switches. I will be using HS to represent them. And the low side switches, in the low side switches your sources are common and they are connected with the negative terminal of the source. So this switch and this switch, they are called the low side switches, right? So when you are going to implement this mode of operation, you will be turning on this switch, so turn on state will be represented by 1 and the turn off will be represented by 0. So this and this switch, they are in state 1, and these two switches are in state 0, they are in the off state, right? And over here all of them are 0, this one, this one, this one and this one, no switch is conducting. And over here this switch is on, this switch is on, this one is off and this one is off, right? And in this mode of operation all the switches are 0, only the diodes are conducting. Okay, so one more thing that we are going to discuss over here, that these two switches cannot be turned on together, and we are assuming the complementary operation at the moment, that when we are going to turn off these switches, we are going to turn on the opposite switches, and S1 and S2 are not turned on simultaneously, right? Okay, so we have these combinations, that high side switch S1 and S3, these are representing the high side switches and these are the low side switches. So if we have 1 over here, this will be essentially 0. Both of them cannot be on together, otherwise there will be the short circuiting, because this is representing the one arm, first arm, and this is representing the state of the second arm. So none of them can be one together, otherwise there will be the short circuiting. So first combination is that the first switch of the high side, that is representing this one. So 1 1 0, the status of this arm, and this is 0 1, right? So 1 0 0 1, so that you can see over here, that is the first state, and that is 1 0 state, and if you apply that one, you are going to get positive voltage, positive current, and your conduction devices conducting devices are the two main switches, S1 and the S4. Okay, then turning off all the switches will apply the negative voltage across the load, that you can see over here. The switch S1 and S4 were on, so once they goes off, all the switches are off, but your load voltage is going to be opposite with respect to that one. This is plus minus over here, this is plus minus over here. Why? Because of the rate of change of current through the inductor. This is going to become negative and the energy is being fed from the load towards the source. So load voltage is negative although all the switches are off. So all switches are off, the load voltage is negative, and your diodes D2 and D3, they are conducting. Current is still positive and flowing in the same direction as it was there in the first state. So the current is positive but the voltage has become negative, and now your diodes D2 and D3 are conducting. Then considering the third state, considering at this one, this is 0 and this one is 1, and this one is 1, this is 1 is 0. So 0 1 for this arm, and for this arm it is 1 0. So in that case, now the voltage has become negative and the current is building up in the opposite direction. So this state is represented over here, that is the 0 1 state. If we look at from the high side switches, the load voltage is negative, and the current, if I look at that one 0 1, if I go back over here, so the direction of the current is like that. So current is negative and the voltage is negative, so power is positive, so it should be negative, right? Okay, so now over here, uh, if I summarize and write it at this diagram for more clearness, so for first arm we have this situation 0 1, and for second arm we have this situation 1 and 0. And so for that one, our voltage is negative, our current is negative, and the switches S3 and S2 are conducting. And in this fourth mode of operation, in terms of binary numbers, this is all the switches are zeros, and voltage is positive, and the current is negative, and power is negative. So it is shown over here in this table, right? So, and these are the waveforms for this full bridge circuit. So now you will have to turn on two switches S1 and S4 by applying the gate voltage, and when you apply the gate voltage, the load voltage will be plus VDC, right? So again, you can represent your inverter with the certain gain K, apply the gate voltages, and you get the load voltages, and we have the source, and whatever is the source voltage, that will be replicated across the load considering the ideal switches, and the wave shape will be of this gate voltage, right? So your switch S1 and S4 will be conducting, and over here S3 and S2 will be conducting when you have one pair of the switch, that is S1 and S4, they are on, so output voltage is plus VDC, and when the opposite pair is on, output voltage is minus VDC. The current waveform will be exactly same as we have already discussed for the half bridge inverter, but over here the thing that is to be understood, this portion, in this portion two diodes are conducting, and in this portion the switches are conducting. So S1 and S4 are conducting. So once you remove the gate voltages from S1 and S4 and you apply the gate voltages to the opposite switches, right? So then first of all the energy stored in the inductor is dissipated. So this portion is representing the conduction of the diodes. D3 and D2 are conducting, and then the current will start building up in the opposite direction. So that is shown over here in this part. Current is building up in the opposite direction. Now your switches are conducting S2 and S2 and S3, and once you remove the gate voltages from S3 and S2 and you shift to this point, it means to turn on the S1 and S4. So first of all, the energy stored in the inductor will be dissipated. So your diodes will be conducting D1 and D4, and then the current will start building up in the opposite direction, right? So this part is shown over here. This part and this part, these are the exactly same. Diodes are conducting. So this will repeatedly happen. So two diodes will be conducting, and two switches will be conducting at an instant of time. And what is the advantage over here? That we are going to get the voltage VDC for the full bridge inverter circuit. However, in the case of half bridge inverter circuit, it was VDC by 2. So you are going to get the double voltage. So what it means, that if you use the source of, let's suppose, 200 volt in the half bridge inverter, so output voltage waveform will be like this: 100 volt minus 100 volt. But if you are going to use the full bridge inverter, so you have the 200 volt supply, so your output voltage will be at plus 200 and minus 200. Alright, so you are going to get the double voltage in the case of the full bridge inverter. Okay, so the voltage as well as the current waveform is not sinusoidal in this case, and in the last lecture we have discussed that for number of applications we require the sinusoidal voltage and the sinusoidal current at the output of the inverter. In some cases the voltage wave shape is very important, and in some cases the current wave shape is important, and in some cases both voltage and current wave shape is important, that is being developed through your inverter circuit when you are converting the DC voltage into the AC voltage or the AC current. So one of the important technique is the PWM technique. So now let's quickly and briefly see the operation of the inverter with the PWM. So we have seen these gate signals before. The voltage that is appearing across the load, the RMS voltage, that depends upon the area under this curve. This part, this one, and this one. This one is the positive area, this one is the negative area. If you look at the DC value will be 0. And if I sketch the source voltage, the source voltage is constant, right? So if I sketch it over here on the same graph, I can say that this is the source voltage. So source voltage is constant, straight line. But what about your load voltage? Positive, and then it is going to become negative, then it is going to become positive. So your load voltage is bidirectional. You can set the movement bipolar. You have the positive as well as the negative portion at the load, but the source was continuously positive. So it is DC and you have converted into AC, alternating current, alternating voltage. Similarly, you can look at the current. The current is alternating at the load, but at the source um, it will be only positive, right? Because if you look at this circuit, so in the first mode of operation, the path of the current is like that, right? And in this mode of operation, again the path of the current is like that. However, if you have the inductive load, then you will be feeding the current uh, energy from the inductor back to the source in the case of the inductive load. If you have the purely resistive load, then there will be no reverse flow of the power, only the power flows from source to the load. But in the case of the inductive load, For some portion, the power flows from the source to the load, and for some time from source back to the load. Okay, so area under the curve is very important when you are looking at the RMS value. It has the DC 0 DC value. DC value is 0, right? But it has the RMS value. And how you calculate the RMS value? RMS value is 1 by time period integrating your function, square of the function over the time period, and then taking the root of that one. So this gives you the RMS value. So for RMS value, as you are going to take the square, so this is going to become, it's already positive, it will become more in magnitude, and this negative voltage is also going to become positive. So if I sketch that one, that I am going to get only the positive area, right? If you look at this part, and when you are going to take the square of this one, so this is also going to become positive. So whole of the waveform is going to become positive, and that will be representing its just like the effect of the DC, right? So RMS value, root mean square value, give you the effective DC, you can say, in the AC circuit. So its effective DC value is there, right? But if you look at in terms of average value, that is going to be 0 in the case of the load voltage waveform, because positive and negative areas are equal. So source voltage is constant, load voltage is changing its polarity, and the RMS value exists, right? So RMS value basically is dependent on the area under the voltage waveform. If that area will be, because you are integrating over here, if that area is large, so definitely the RMS value will be increasing, and if you reduce the area covered by this voltage waveform, so then the RMS value will be decreasing. So RMS value depends upon area under the curve. If you cover more area, you will be getting more RMS value, and if you reduce the area that is covered by the voltage waveform, so the RMS value of the voltage will be reduced. So if you develop a mechanism that you change the area at the load voltage, and how to change the area under the load voltage, you will have to control the area that is covered by the gate voltage waveform. Now if you convert it into like that, let's suppose a set of train pulses of the train, sorry, a train of the pulses, if you have like that, so if we have like this, so what about the area under this waveform, which consists of these pulses? Now you have only this part, right? So you have reduced the area with respect to the waveform that was covering the whole of that. So if instead of using the constant gate voltage, I use a pulse train, so I can control the area of the gate voltage, and that will be reflected on the load side. So load voltage is going to become like that, because once your switch, pair of the switch is turned on, you have the output voltage, otherwise the output voltage is going to become 0, right? So your load voltage will be like that. So now if you change the width of these pulses, area under the curve will be changing, right? So for one pulse, let's suppose that you have this one, and if you update this pulse like that, you increase the on time, so more area is covered in this waveform, and if you further increase the width of the pulse, more area will be covered. So when the area covered will be increasing at the gate, so area covered will be increasing at the load, so more voltage will be there at the load terminal if you will be increasing the duty cycle. So if you increase the duty cycle of this pulse, because we are going to convert it into that one, we are, instead of applying the constant voltage, we are going to apply a train of pulses, right, a PWM signal. So once you change the duty cycle of these pulses, gate signals, so the area covered by the gate voltage, that will be changed, and at the same time the output voltage will be changed. So that is shown over here in this diagram, that instead of applying the constant gate signal, we are going to apply the train of pulses, and I am going to highlight to make it clear. This is the set of pulses, right? So for half cycle we have set of pulses, and for half cycle the switches are in the off state, opposite switches will be turned on. So I am going to highlight this one over here. We are going to apply these pulses. So when we will be applying these pulses, so what about your load voltage? So when you will be having the gate voltage, your load voltage will be there, otherwise your gate voltage, your load voltage will not be there, it will be 0, that you can see over here, 0 voltage, and over here VDC. So your gate voltage will be amplified, and that will appear at the same pattern at the load terminals, right? So now if you change the duty cycle of these pulses, duty cycle is updated, it means area under the curve is updated. And if the area under the curve is updated, so just look at this one, RMS value will go up if we are going to increase the duty cycle. So duty cycle is increased, it means area covered will be increased, and it means RMS value will be increased. And if you decrease duty cycle, the RMS value will be decreased. So how to convert your constant gate voltage signal into a PWM signal? That can be done easily if you have the constant gate voltage signals that we have discussed for the half bridge or the full bridge. So if you take a PWM signal that you can see over here, PWM signal that is of high frequency as compared to your output frequency. So this constant voltage gate signals will be representing your output frequency, right? And if you take a high frequency signal that is shown over here, and if you perform the AND operation of this pulse with the constant gate voltage signal, so that constant gate voltage signal will be converted into the PWM signal. So let me show you over here in detail that what is going to happen. You have you can say a train of pulses. This is our PWM signal, and we, let's suppose, have the constant gate voltage 50% duty cycle signal. Both of them are applied at the input of the input 1 and in input 2 of the AND gate. So what will be the output? The AND gate gives you the output when both of the signals are 1. If any one goes to 0, there will be no output. So this will be the signal. So if you have this constant voltage, you can say envelope, that is going to be applied on the gate of the switches, and you perform the AND operation with this signal, AND operation of this one with the PWM signal. This is the PWM signal. So if you perform the AND operation, what you are going to get? You are going to get this set of pulses, and these set of pulses are applied at the switches gates. So what is going to happen? Your load voltage will be exactly following your PWM signal. And over here this is 0. So when this becomes 0, so what about the output of the AND gate? That is going to become 0. So that you can see over here that no pulses over here. Why? Because the gate voltage is 0. Even if you have the train of pulses, but output will not be there. No pulses at over here. Why? Because your gate voltage is 0. 50% duty cycle is to be ensured. Right, again, once the gate voltage is high, you have the pulses over here, so output will be in the form of the pulses. And same is applicable for the second set of the switches, S3 and S4. You take this signal that we discussed for the half bridge and the full bridge, and you are going to perform its AND operation with the same PWM signal. Right, so at the moment let's assume that this PWM signal is of high frequency, number one, and the width of the pulse is same in every cycle. It means the duty cycle is fixed. The duty cycle is fixed for one cycle. So we usually call it the constant PWM because we are not changing the width of the pulses. Whatever is the pulse width of one pulse, same is the pulse width over here, same as the pulse width over here, and so on. Pulse widths are same. Okay, so now let's look at the current waveform. When you will be turning on the switch, the current will be increasing. Let's consider this gate pulse. This gate pulse has been applied, right? So correspondingly the current will be increasing. And once that gate pulse is not there, you are at over here 0 voltage, so the current will be decreasing. And once you apply the gate voltage again, that you can see over here, gate voltage is applied, so what you have? You have the rising current. Then 0 volt current will be in decreasing, then plus VDC, so current will be increasing. So you will be observing the current waveform like this in this case. So what is the advantage that you are going to get over here? You are changing the area under the gate voltage waveform, and that is reflected at the output of your inverter, that is of higher voltage VDC. So once you control that area, you can control the area under the curve, and area under the curve will control the RMS value. So you can control the inverter output voltage with the help of the PWM operation. So the maximum voltage will be there when you will be covering this uh, whole area. If you cover this whole area, maximum RMS value will be there. So it means the RMS, the square wave operation, pure square wave gives you maximum RMS value. Once you introduce PWM, RMS value is reduced. Why? Because the area under the curve is reduced. The maximum area is there with the square waveform. So with the help of the PWM operation, you can reduce the RMS value at the inverter output. So if this set of train set of pulses, the all the pulses are of equal weight, same duty cycle, then it's the constant PWM operation. The other way that we have to have the varying pulse width, PWM, as you can see over here, the pulse width is not same it is changing, and it is changing according to the sine wave that you can observe over here. As the magnitude of the sine wave will be changing, the width of the pulses which are being applied at the gate of the switches, that is going to change. Means duty cycle is not fixed, it is varying according to the magnitude of the sine wave. Let's suppose when the magnitude is higher, you have the higher width of the pulse, and when the magnitude is decreasing, you can see the width of the pulse is decreasing. So when you have peak, you have the maximum width, and once sine wave is approaching to 0, the pulse width is going to become 0. So this is said to be the sine PWM, sinusoidally pulse width modulated signal. The width of the pulses is changed according to the magnitude of the sine wave. So what will be the advantage of using the sinusoidal PWM? The advantage will be that your this current waveform will be approaching to the sinusoidal waveform. So your current, we can say, will be improved and finally will be approaching to the sinusoidal signal if you apply the sine PWM, means the varying weight signal, and how the width of the signal is changing according to the magnitude of the sine wave. That's why we are calling it the sine PWM. So the voltage waveform is in the form of pulses, but the area that is changing across the load because of these pulses is sinusoidally varying, because you can see when you have the higher magnitude of the sine wave, you have the more width, more area is being covered. So the area variation is according to the sine wave. The voltage is in the form of pulses, and that is this one, VDC plus VDC 0, then plus VDC 0, and over here minus VDC and 0. So the voltage, there are three voltage level, you can say, plus VDC, minus VDC, and the 0 volt in the case of PWM operation, right? This PWM operation. So current waveform, the resultant current waveform will be approaching to the sinusoidal waveform with the sine PWM operation. When you vary the width of the pulses, the width of these pulses according to the sine wave, then the current will be approaching to the sine wave. The voltage waveform will be in the form of pulses, but the width will be changing according to the magnitude of the sine wave. When its peak, its magnitude is more, sorry, the width is more, and when the magnitude of the sine wave is decreasing, the width of the pulse is also decreasing. So varying pulse width in the case of the sine PWM. So voltage area effect is sinusoidal, wave shape is not sinusoidal, but the current wave shape will be approaching to sinusoidal in the case of the inductive load. So for resistive load, the current waveform will be exactly same as that of your voltage waveform. Whatever is the shape of the voltage waveform, same will be the wave shape of your current waveform for the resistive load. But if you have the inductive load, then you can make the current sinusoidal, right? So that's why we call it the sine PWM, and in sine PWM, our load voltage in the case of uh, RL load will be approaching to the sinusoidal waveform because of the sinusoidal variation of the voltage area that is covered in the positive and in the negative cycle. So we have seen two types of the PWM techniques. One is the constant PWM. In constant PWM, there is no variation of the duty cycle, right? One PWM signal is generated and its AND operation is done with the gate signals, and the gate signals are converted into the PWM signals, and your output is converted into the PWM signal, and current will not be approaching to the sinusoidal. But what is the advantage of that one? You can control the voltage, you can control the RMS voltage across the load, because that is the function of the area under the curve. But if you vary the width of the pulses according to sine wave, you can vary the voltage. You have the voltage control, because you are going to control the area under the curve, and that will be controlling the area under the load voltage waveform, and the RMS value will be changed, but at the same time your current will be smoothing and will be converted into the sine wave. So in the sine PWM you have the voltage control and the control of the current waveform, but remember you can reduce the voltage with this PWM as compared to a square wave. You have the maximum area covered under the square voltage, a square wave voltage waveform. So square wave gives you the maximum possible RMS value. You can decrease the voltage with respect to that. Okay, so let's wind up our this video. And if I summarize, we have discussed the half bridge inverter, and then we have discussed the operation of the full bridge inverter circuit, and then we have seen that how we can use the PWM to control the load voltage, and in the case of RL load, how we can control the wave shape of the current. So that's all from this video. In the next videos we will discuss more about the operation of the inverter circuit and about the quality performance of the inverter circuits. Thank you very much.